Example 1.16 is going to really start the abstractifying of the algebra that we're going to be experiencing in this course. Now, the example starts with defining a function in the same way that we've defined all of our functions thus far. There's an equation. We have a name, a first set, and a second set. So we have all the elements that we would normally need for a mapping, but it also has some extra information. It says, and A, comma H are elements of the real number. So what this is saying is that A and H are not just letters. They are there to represent a particular real number. We just don't know exactly which real number it is. So it's not to represent all of the real numbers. It represents a very specific real number. So A is any real number that we can think of, but H is not going to be just any real number that we can think of. It says that H is not allowed to be 0. So you can think of any real number that you want except for 0, and that's what H could potentially be. So this is the abstractifying part where we have to really allow ourselves to visualize A and H as not really letters, but really as representatives of a real number that meet the criteria that are provided. So for the first evaluation, it says f of A. Now certainly, when we look at our mapping notation, it says that we're supposed to be using real numbers. Does A qualify as a real number? Well, according to what it says up here, A does represent a real number, so I'm allowed to proceed. I know it feels a little strange to do this without having an actual real number there and only having its representative, but that's what we're going to do. So this is going to say 2 times A squared plus 3 times A minus 1. And it looks just like what we would do on example 1.14 or even 1.15, where we would just take a value and substitute it in. So when we simplify, we'll find that there are really not a lot of simplifying things to do. So A squared is just going to be written as A squared, and then we multiply it by 2. We just call it 2A squared. Same idea for 3 times A. We just call that 3A, and then we'll subtract 1 there at the end. Nothing else can simplify, which means this is the answer. So that means that A maps to 2A squared plus 3A minus 1. And I know it seems incredibly strange and it feels a little weird to do that, but when we allow A to represent a real number, we are allowed to do that. Take a look at part B. It says f of negative A. Now, when you see a negative symbol like this, what that really represents is the opposite of whatever you have here for A. So if we know that A is supposed to represent a real number, then the opposite of a real number is also still a real number. So we can proceed with taking negative A and substituting it in to the equation. So that'll end up giving us actually the same first term that we had with f of A. When you take negative A and square it, it ends up becoming a positive A squared. So it's going to look identical. It's going to say 2A squared. And the second term says 3 times negative A, which can be interpreted as a subtraction of 3A, and then I still have minus 1 there. So when you start looking at comparing the answer from part B and the answer from part A, they look almost identical. The only place where you see even a little bit of difference is right here with the operation. We have an addition operation versus a subtraction operation. But other than that, they're identical. Part C, however, is going to get us into a more involved version of this, because now we have to think about not just A, but also H. So when I'm looking at a plus h, I have to think about, okay, a represents a real number, h also represents a real number. If I add those two things together, do I end up with another real number? And the answer is yes, you do end up with another real number. So I can proceed with using a plus h as a element, as a real number. So since I'm thinking of a plus h together as a real number, when I input and I substitute in, I have to substitute in the a plus h together. So it's going to be 2 times a plus h squared plus 3 times a plus h minus 1. And when we do this, we have to be aware of what it means by definition to actually square something. So to actually square something means to repeat the multiplication of that value twice. So I can't get away with just squaring the individual terms inside of the a plus h, but rather I have to think of it as a plus h times a plus h plus 3 times a plus h minus 1. So when I look at it from this perspective as just a repeated multiplication, then there's going to be a series of distributions that have to take place in order to get the individual terms realized. So the first step in the first term is going to be to go and go through all the distributions of a plus h times a plus h. So that's going to be a squared plus ah plus h squared. Then the second term has another distribution, 3a plus 3h, and then the constant just comes down as minus 1. And when I look inside the parentheses of the first term, I can see that there are two terms inside of that are considered like. So I'd want to combine those together and get 2 times a squared plus 2ah plus h squared. And then I'll copy down all the other terms because none of them are considered like, so I can't do anything further with them. And then the only last step here would be now to distribute 2, and that would complete that first term. My resulting terms will be 2a squared plus 4ah plus 2h squared plus 3a plus 3h minus 1. And you can check and you can see that you now have 6 terms, but none of them are considered like. Since none of them are considered like, this ends up being the final result. That's the final answer there. That is what a plus h would map to. Now I want to take in part D some of the results that we just came up with, and I want to put it into an expression that I've created for us to practice with some of the algebraic simplification. So for part D, I have f of a plus h minus f of a all divided by h. So when I go to set this up, I'm going to set it up by opening up a parenthesis, and we've already calculated f of a plus h. F of a plus h is given down here as 2a squared plus 4ah plus 2h squared plus 3a plus 3h minus 1. We already have that result. But the next thing that comes in this expression is a subtraction sign. That would be this subtraction sign right there. So I want to take that subtraction sign, put that into my expression, and then I'm going to open up another parenthesis because that's where I'm going to put the expression for f of a, which we've also already done. We did that over here in part A. So that's going to give me 2a squared plus 3a minus 1, and all of that will have to be divided by h. So the cool thing here about this particular expression is that we're going to be taking everything from this grouping and we're going to be subtracting it from this grouping. So essentially what we're doing is polynomial subtraction. So anything that is the same, any terms that are the same within your two groupings are just going to eventually cancel out because of the subtraction. So for example, 2a squared and 2a squared are going to cancel out. 3a minus 3a goes away. -1 minus -1 goes away. So what looked like a pretty involved expression is going to simplify to just have 4ah plus 2h squared plus 3h all divided by h. But there's still a little bit more that we can do here. Now if you look at the numerator, every single one of those terms, there's only 3 terms now in the numerator, all 3 of them have a common factor of h. So you can apply your greatest common factoring technique and you'd have h times 4a plus 2h plus 3 all divided by h. And that now allows me to be able to cancel out the h's, because remember, h just represents a real number. So if I have a real number in the numerator and the same real number in the denominator, I can cancel them out just like I'm simplifying a fraction, the idea of reducing a fraction. Same concept. So now I get a final expression of 4a plus 2h plus 3, but one of the stipulations that we had was that h was not allowed to be 0. So when I canceled out the h's, I sort of lost the identity of h a little bit, and so I want to go back and make sure that it's represented, and this ends up being the final representation for this expression after it's simplified. And this is not just a generic expression that I created. It actually does have a name. It's a special type of expression. This expression right here is called the difference quotient. And mathematicians are known for naming things appropriately. So the word difference you should associate with the subtraction operation, and the word quotient you should associate with the division operation. And certainly that's precisely what we have. There is a subtraction, and then the fraction bar represents a division, hence why we call this the difference quotient. There will be much more about this in a later section, but I wanted to give you a preview of coming attractions, and it gives you an opportunity to be able to use the evaluations that you did from parts A and C and put them together into another expression.